Hello,
Hello,
everyone.
everyone.
This is
This is
Linguistics
Linguistics
487.
487.
Um,
Oh,
boy,
boy.
laptop. Um, so this is the course is it's mathematics and philosophy in linguistics. It's not mathematics and philosophy for linguistics. We'll see that there are lots of ideas and concepts um, about structure in mathematics and philosophy, which is very relevant to linguistics, and that's the purpose of the course. um, and this short video for about half an hour is is a recap of the material that we've covered before for the midterm exam, and also for future reference. So basically, what we're studying in this course is from the perspective of mathematics. You're studying mathematics of non-embedding structures in language. Typical examples will be like morphology, and phonology. Um, the reason I say, say that is that, for instance, there is no morpheme within a morpheme. There is no word within a word. There is no syllable within a syllable. So these are non-embedding structures in language, but structures nevertheless, and we need to understand their aspects, mathematically speaking. And there are, of course, embedding structures in language. Most predominantly syntax and semantics. Um, so the first part is what we have covered in 6 or 7 weeks. The second part is is going to be covered in the remainder 6 or 7 weeks. Just to give you a recap of the first part, um, um, the reason why we're studying linguistic structures as mathematics is essentially it's about the nature of mathematics. Mathematics essentially attempts to see the invariant in linguistic structure. Crucially, we are not mathematicizing linguistics. Okay, we're saying mathematics is a good way of understanding if you, universal structures or invariant structures, if you want to talk about it mathematically. And then you can talk about whether these invariant structures are empirically psychological objects, physical objects, or mathematical objects, or abstract realities And see that these are essentially um, uh, ways to understand mathematical principles underlying the universal, and then you worry about the empirical aspect of the universal. So that's one idea. Um, and for that, uh, we need a representation. If you're going to do this mathematically, you need an abstract language to do all this. Um, um, and this is what we call grammars. So from that perspective, some grammars are non-embedding and some grammars are embedding. And if there's a difference in mathematics of embedding and mathematics of non-embedding, this is something important because you capture the invariant of the embedding and the invariant of the non-embedding. And if you talk about the philosophical connection of this, it says this is mathematics. If you're doing mathematics, if you're doing mathematics, then it's the mathematics of what is the crucial connection. Sorry about the noise. Um, this is the philosophical connection, sort of. So this could be the mathematics of sound patterns. And if you go this way, your grammar is just a sequence of sounds. You're essentially, in philosophy, you consider it a nominalist. Okay. Or you could be like mathematics of uh, psychological objects. If you're going this way, you will be a conceptualist. This terminology is quite well set up. It's a classic since Jerry Cott's work in the 70s and 80s. I'm just summarizing from them, and I'll add more to it as we proceed. Um, or you can think of this as the mathematics of abstract objects. In other words, your elements of grammar are essentially objects. It's just that they're abstract. And if you're following this tradition, you would be a realist. Okay. And more recently, this could be mathematical of biological objects. This has also been claimed in linguistics, and this would be like biolinguistics program. And the reason I'm mentioning these at least four brands of philosophy of linguistics is that when you capture the mathematical invariant, it's essentially an abstract capture of the ideas about linguistic structure. And then you worry about the empirical basis of that linguistic structure. And this is when you go into these more or less four positions in the empirical significance of what you're saying from a philosophical perspective. um, so what we've seen so far is essentially we're studying mathematics of non-embedding. And the way we talked about mathematics of non-embedding is we there is what is called regular languages. These are the kinds of languages which can be described by very simple set operations like union, concatenation, and clean star. And if you notice these three operations of of regular structure, they are essentially memoryless. That's why they are non-embedding. Okay. Unlike intersection and difference, where you need to remember something to get something else. Okay. So it's important to know that there is a certain kinds of mathematics to go with this. And if you think of regular languages, it which is another way of saying regular sets, this is a level of abstraction in mathematics where a set with certain properties and allowing only certain kinds of operations has its own niche in linguistic theorizing, and this is important, at least for morphology and phonology. Okay. And we have also seen that for any regular language, there is a regular expression describing that language. There is a finite automaton. Uh, uh, this could be non-deterministic, like NFA, non-deterministic finite automaton. It could be deterministic finite automaton. um, and the important point of this is like this thing you can think of as description. Description of structure. These you can think of as computation of structure. And the whole point of calling this mathematics meaningful for non-embedding is that these are actually connected. You can go from description to computation and from computation to description. And that gives you an adequate level of understanding the mathematics of non-embedding. Okay. We have also seen that for any non-deterministic finite automata, there is a DFA which is weakly equivalent to it. Weakly equivalent means they recognize the same set, but not necessarily the same way. If they recognize the same way, same set, and do it the same way, then they will be strongly equivalent. But that's not what the argument is. Okay. Um, and something I have not covered in class, and I'll probably not cover it, is for any regular language, there is a minimal DFA. In other words, um, regular languages are uniquely identifiable by a by a minimal. If there's a minimal DFA, then all other DFAs are essentially equivalent to that. Um, um, the importance of that for the mathematics of non-embedding is that this means that um, 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 the structures that we're dealing with here are so simple that they can be uniquely identified. Well, you cannot say the same thing for syntax and semantics because of ambiguity, self-embedding, and others. But for this level, that seems to be the important property, and these can be shown to be mathematically complete and sound. There are theorems for that, but I'm going to not talk about this. And in going from description to computation and from computation to description, we've seen two things, and one, uh, for any regular expression, let me just write regular expression, there is an NFA recognizing the language of the same language of the expression. Okay, and this is the simplest way of showing this is called Thompson's construction. And the idea in Thompson's construction is if you look at regular expressions, what is regular? Well, if alpha is regular, then alpha or beta is regular. Then alpha beta is regular, and alpha star, and of course, beta star are regular. Okay. Um, and NFA construction of this, just to give you a sketch of this, assumes that if alpha and beta are regular, then there is actually an NFA for them. Let's call the first one M alpha, the other one M beta. If these are machines, then the way you construct the machine for alpha union beta is you set up a new start state and then go to the start state of this state using empty transitions, or to this using empty transitions, and you accept whatever that machine accepts or that machine accepts. So you'll be, because you can go either this, that way, or that way, you're essentially saying the language of this NFA is the union of the language of these two NFAs. And I've shown in class how you can do the machine for others. So for instance, if you do alpha beta, and since they are regular expressions, then there must be machines for them. Let's just call them M alpha and M beta. To construct a machine for M alpha beta, you start here, go to the beginning of M alpha, and from the end states of M alpha, you go to the start state and you accept. In other words, the end states of M alpha are no longer uh, end states in alpha in a machine for alpha beta. So end states of M beta are the end states. You can see that this is actually concatenation because it essentially means the first box means do M alpha, and from the end states it says go to MB, M beta, and do M beta. It's essentially alpha beta. And you can see the star, if this is M alpha, then if you go to beginning states of M alpha, and from the end states, if you go back to uh, 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 beginning state and make the beginning state accepting state, then you can accept this is the machine for M alpha star because you can accept 0 or more sigmas using this machine. This is the Thompson's construction. Okay, so we know that you can go from description to computation, and we have also seen that from computation to description, it is also a very simple method. There are different ways of doing this. The way the textbook does is from NFA first. You first design what is called a generalized NFA. It's generalized in the sense that it's a GNFA is in a normal form. What does that mean? Well, that means no incoming arcs to start state. No outgoing arcs from end states. Start and end states are different, and every other state has transition to all other states. And we can see that you can put any NFA in this normal form. Why are we doing this? It just NFA essentially relaxes the problem. In other words, it first complicates the problem by making your NFA more complicated. But by doing so, it tries to make the conversion from NFA to a regular expression easier and compositional. Usually in sciences, relaxing the problem is more than that. It can not only make it more complicated so that it can be compositional, you also make some non-instances as instances of the problem and then fix it later, but I'm not going to get into that because that's not what we're doing here. So what does that mean exactly? let's take let's take an NFA. Uh, it's just a simple NFA. Okay. Um, um, Now, what's the thing about what's the property of this NFA? It's not in normal form, in canonical form. Why? Because there are incoming transitions to the start state. Okay, and there are outgoing transitions from the accepting state. So you have to put it in GFA notation. So what you do is you make up a new start state. Let's call this state Q0. This one is Q1, let's say. And then your Q0, this is your new start state, and you just go to Q0. And now you can have these outgoing transitions from Q0 to Q1 because this is no longer your start. Q0 is no longer your start state. Okay. Um, uh, but now your start state is same as your end state, and that's not GFA. So what do? You make your start state a non-accepting state. You make another accepting state, go to a sigma. And in the other ways, you just say Q0, A, Q1, B, A, B. Um, okay. Um, uh, and then you connect that. So the idea is now my start state, this one, and my end state are distinct. And every other intermediate state has transition between all of them. So this is Q1 on Q1. This is Q0 on Q0. Q0 can go to Q1 and Q1 can go to Q0. So what you do, the process is that once you come to this point, you can eliminate everything but the start state and end state by rewriting them simpler and simpler. Okay. Um, so that's the idea. And one example to do this, there are lots of examples. It shows a step-by-step construction of a GNFA and then getting the regular expression for this by simplifying the states in between. The point of all this is that at this point, you come to an understanding uh, regular expressions, NFA, DFA, and their equivalence. This gives you limits of non-embedding. And that's relevant to morphology and phonology. So I'm going to talk about that in class. Um, and this we reach by um, uh, having a mathematics of the invariant for non-embedding structure. All right. So that's what we achieve. And then in the second half of the book, of the course, we're going to look at embedding structures. First, we're going to talk about syntax and context-free grammars, which are essentially the formal equivalents, formal precursors of what is called phrase structure grammar in linguistics. And then we're going to talk about lambda calculus uh, to to show how this embedding can be done in semantics as you do syntax. Okay, that's the remainder of the course. So that's essentially the summary of what we've done so far and with what we're going to see in upcoming weeks. All right, so I'll stop the recording and see you soon.